Hi, in this video I want to show you how to do another type of chi-squared distribution hypothesis test. And this concerns tests of homogeneity or tests of independence. In these types of problems, you're going to have a set of data that's sorted into two different categories. And typically that data is presented in what's called a two-way table or a contingency table. If we refer to one set of categories as the row variables and another set of categories as the column variables, the null hypothesis for these tests is that the row variables and the column variables are independent. And that would be a test of independence. In the case of tests for homogeneity, the row variables might be different populations, and the column variables might represent proportions of some quantity that can take different values, and you're looking to see if those proportions are consistent across all of the populations, or if the column variables differ from one population to the next. Regardless of the type of test it is, whether it's about independence or homogeneity, the procedures are exactly the same. You start with, as I said, your data sorted into a two-way table or contingency table, and in this example that I've set up, I have a matrix of data, and this concerns the transactions done at a coffee kiosk at various times of the day, morning, afternoon, or evening, and whether they were cash transactions or credit card transactions. And the question is, at the 5% level of significance, is there a difference in the way customers pay depending on what time of day it is? In other words, is there evidence to indicate that the method of payment is independent of the time of day? Are people more likely to use credit cards at one time of the day, such as in the afternoon, than at other times of the day? That's what we're going to test. Now, to do this on the TI calculators, we're going to use, in the Stat menu, I'm going to go over to the Test submenu, and I'm going to look for the function called chi-squared test. And this is a function that's on both the 83 and 84 calculators. And I'm going to scroll up to the bottom, and then you'll see on the 84s it's item C in the menu, and on the 83s it would be, I believe, item B. So I'm going to select that and press enter. And you can see the inputs for this test are basically two matrices. You have matrix A of the observed values and matrix B of the expected values. So before we begin this test, I need to show you how to enter this set of data in this two-way table into a matrix on your calculator. And this is a pretty easy thing to do. So what I'm going to do is go into the matrix menu, and that is the shift function over the X inverse key. Okay? And you've got three submenus in the matrix menu, and I'm going to go over to edit, and I'm just going to work with matrices A and B for this example. So matrix A is going to be where I'm going to put my observed values, and the observed values are the ones that are given to me in the table. So I'm going to press enter, and the first thing you need to do with a matrix is to dimensionalize it, and that means to tell how many rows and how many columns. And the first quantity here is the number of rows, and that's 3. And then I press enter, and then I'm going to tell it 2 columns. And now it configures the matrix to these dimensions. And now all I have to do is type in the values as they're shown. And I press enter between each value. So I go row by row, and then I've entered all 6 values. What I'm going to do now is go back to my test function. You'll note that or you may recall that the expected values, when you do these types of tests, are based strictly on your table of observed values. In other words, you would be computing the row totals and the column totals, and then you would be using those quantities to compute the expected values for each of these cells. Well, that's a fairly lengthy computation. It's not difficult, but there's a lot of steps involved, and one of the good things about using your calculator is that it will do those computations for you. So you only need to enter the observed values in matrix A for this test, and it will compute the expected values and put those into matrix B. So I'm going to just use my keystroke shortcut alpha C to retrieve the chi-square test and put it on my main window. Again, I have matrix A, which we just configured. Matrix B, I didn't even need to dimensionalize. I just indicate that's where I want those values to be stored, and then I press calculate. And what it returns is first the test statistic chi-squared, which is about 2.8, and then the p-value for the test, 0.2465 approximately, and the degrees of freedom, which is 2. And then if you go back and look at the matrix, if we look at matrix B, you can see it was dimensionalized to a 3 by 2, and these are the expected values that it computed based on the row totals and column totals. So that's basically how to do a chi-square distribution test when it's a test of independence or test of homogeneity and you're given a two-way table of data. So it's a very straightforward calculation to do. Let's do one more thing and take a look at the other option with that test. Here again I have my two inputs, A, B, and let's just take a look at what the draw function does. And basically what you're seeing is a chi-square distribution for 2 degrees of freedom, and what's shaded would be the p-value, which is indicated down here, as well as the test statistic. Okay, so that's all I wanted to show you about doing chi-square tests of independence or homogeneity. It's a pretty straightforward function. As always, it's a good idea to do 1 or 2 of these types of problems by hand first, so you get a feel for what it is exactly that the calculator is doing for you, and gain an appreciation of how many steps you're saving by doing it this way.